Hello everybody and welcome back. In this video we are looking at question number 4 on this Ontario Senior Math Competition. So what have we got for question number 4? I showed it to you at the end of the last video, question number 3, but what have we got here? Let's actually read it out this time. Prove that the expression x to the 5 over 5 plus x to the 3 over 3 plus 7x over 15 is always an integer for all positive integral values of x. Okay, so I've seen some questions like this in the past. This is going to end up being some modular arithmetic work. First thing I want to do, I want to combine this into a nice single expression. The reason being we don't want to be dealing with parts of this, because if you just look at x to the 5 over 5 on its own and you say plug in x equals 2, you'll get 32 over 5, which isn't an integer. So you have to combine it with the other parts. So we really want to be looking at this thing as a whole expression. So I see a 3, a 5, a 15. 15 would be a great common denominator. So let's get that going. So that'll be 3x to the 5 plus 5x cubed plus 7x over 15. So this is an integer, which is what they want me to show, exactly if 3x to the 5 plus 5x cubed plus 7x is a multiple of 15. So I don't need to worry about the 15 down there as long as I can show that this is always a multiple of 15. And here's where modular arithmetic is going to help us out. Okay. First things first, I'm going to take out a factor. As many factors as I can. I'm definitely going to take out a factor of x. Can I do more? We've got a quadratic here. Can I factor to the 3, the 5, and the 7 make me think maybe I can't, but let's, negative. So x squared would be negative b plus or minus b squared minus 4, that's going to be 25 minus 84. That's not going to be positive. So no roots to be had here, sadly. So this is as good as I can get it. That's not terrible. So now we got a choice to make. Really wish that factored more. Usually when I've seen questions like this, the factor's a bit more. I don't think this is going to be too terrible. They all tend to follow the same pattern. But the question is, all right, so I need to show that no matter what x I pick, this is a multiple of 15. Now that's a hard thing to do because you might have to consider all numbers everywhere. But what we can do is we can look at this expression one of two ways. We can look at it mod 15, in which case you just need to look at what x is. It's x 0, 1, 2, 3, all the way up to 14. Mod 15, and if you can show that all of those work, give you 0 if you're working mod 15, then the whole expression is. Or we could say, well, 15 is 3 times 5. So let's show that this expression is always divisible by 3, no matter what x I pick, or always divisible by 5, no matter what x I pick. And it's going to be about the same amount of work either way. I think I'm going to go with the 3 and the 5, if only because this part here and this part here will go away pretty quickly for at least one of them. Okay. So tell them what you're going to do before you do it. We'll show 3x to the 4 plus 5x squared plus 7 is always a multiple of 3 and 5, no matter the x. And I'm going to tell them how I'll do it by working modulo 3 and 5. Okay, so first up, let's do 3. So in mod 3, x is either 0, 1, or 2. What we mean when we say this, in case you're not as familiar with modular arithmetic, basically we're saying x has a remainder of 0 or 1 or 2 when you divide it by 3. And that's it. That characterizes all integers. And we can also see that 3x to the 4 plus 5x squared plus 7, well, mod 3, 3 is the same as 0, so we can get rid of that. 5 is the same as 2, and 7 is the same as 1. So this will help our work. Okay, so here's what I want to do. We'll say our x value, and then 2x squared plus 1. So x is 0, or it's 1, or it's 2. And then we'll talk about the product. Okay. So if x is 0, x squared is going to be 0, so 2 times 0 is 0, plus 1 is just 1. If you've got 1, 1 squared is 1, times 2 is 2, plus 1 is 3, but there is no 3, so we'll say it's 0. Notice the product here, 0 times 1 is 0, 1 times 0 is 0. 2 squared would be 4, except we don't really count 4. 4 has a remainder of 1, so 4 and 1 mean the same thing, mod 3. So 2 squared is really 1, times 2 is 2, plus 1 is 3, except there is no 3, so it's a 0 again. So we can see that the expression we're talking about is congruent to x times 2x squared plus 1, which is congruent to mod 0 mod 3, regardless of x. And we're just going to do the exact same thing mod 5. Okay, so x is either 0, 1, 2, 3, or 4. Mod 5, you get some more remainders when you divide by 5. Now, sadly, the x to the 4 won't go away. I think you could probably do something with Fermat's little theorem right now, but I don't particularly care to try and remember that right now. Let's say 3x to the 4. This goes away because 5 is the same as 0, and 7 turns to 2. So we'll make ourselves a little chart. X, and then 3x to the 4 plus 2, and then the product here. So x is 0, or it's 1, or it's 2, or it's 3, or it's 4. If it's 0, then this will be a 2, but the product is 0. If it's a 1, x to the 4 is 1, times 3 is 3, plus 2 is 5, except there is no 5, it's 0. 2 to the 4 is 16, but 16 leaves a remainder of 1 when you divide by 5, so 2 to the 4 is 1 mod 5, times 3 is 3, plus 2 is 0. 3 to the 4 is 81, which leaves a remainder of 1, times 3 is 3, plus 2 is 5, which is 0. 4 to the 4 is 256, which again leaves a remainder of 1, times 3 is 3, plus 2 is 5, 0. And these products all turn out to be 0 as well. Okay, looks like x to the 4 is almost always 1, regardless of what I pick. Unless you're talking about 0. Of course, 0 to the 4 is 0. Okay, so what's our conclusion there? Well, the expression we want to talk about is congruent to the expression we did talk about. And I showed it's always congruent to 0 mod 5, regardless of x. So this is always a multiple of 3 and 5, therefore a multiple of their lowest common multiple, which is 15. And so my final conclusion, the expression that they asked me for, rewritten the way I did it, is always an integer. And there we go. We proved what they asked me to do. Okay? I'm not aware of another way you could approach this question. These ones tend to be modular arithmetic, show that this is always a multiple of 7, show that this complicated polynomial expression always leaves a remainder of 2 when you divide by 14, that sort of a thing. If somebody has another way to do this, I'd be more than happy to read about it down below, even if you just gave me a hint, try this. I would love to try something new for this question. But that's it. That was question number 4 there. And by the way, that goes the same for any other question. If you did 3, as I was mentioning in the last video, if you did 3 using calculus in the video for question 3, leave me a little note as to how you did it and how it went. I'm more than happy to learn new ways to do questions. I love learning new ways to do questions. Okay, that's it for question 4. Up next, question number 5. Thank you guys so much for watching, and I'll see you for question 5 next time.